Hi everyone. This first thing I'm going to show you doesn't really have anything to do with probability other than that you probably will have difficulty with it if you've never seen it before. So hit the pause button until you spot the mistake. Okay? I'll wait here until you find it. Still haven't found it? Let me give you a hint. I'll give you a big hint. It's got actually absolutely nothing to do with the numbers. I thought it had something to do with the numbers when I first saw it, and I thought maybe it had something to do with the sequence of the color of the numbers, like maybe it's not the right sequence for the rainbow or something like that. So big hint, has nothing to do with the numbers. So keep looking, pause and keep looking. Still haven't found it? All right, I'll give you the biggest gigantic hint I can give you. In fact, this will absolutely give it away. If you still haven't seen it, I want you to read that sentence out loud, one word at a time. Ha 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 ha, now you found it. Okay, so if you've never seen something like this before, and even if you have seen something like this before, I've seen puzzles like this before, I still fell for it. It took me a long time to get it. Now, I'm going to reassure you, if you were like me and it took you a long time to find it, I think that's the mark of a good brain, all right? Not a weak brain. Why? Your brain's got lots to do. It's got to take shortcuts whenever it can, and we'll see that later in this presentation. The brain is always looking for a shortcut. Excuse me. So we generally, when we get good at reading, don't literally read every single word. We start to learn to recognize whole sentences at a time. Okay? Big globs of words, if nothing else, at the same time. And when two words are separated like that by space and they happen to repeat, well, we have a hard time seeing that because we're kind of catching the whole sentence and not reading each word one at a time. So congratulations if it took you a long time to find it. Probably means that you got a good brain that likes to take shortcuts. I don't know if that's a good thing or not. I'm going to think of it as a good thing. Okay, let's move on. We're going to talk about probability here today. And those of you that took a math stats class before know this very well, that you spent a lot of time on probability, and thankfully you're going to see that this is a rather short presentation, and it's about all I'm going to directly have to say about probability. So we're going to cover it a lot quicker than you typically do in a math stat class. That's one of the biggest differences between psych stats and math stats, okay? They get really hung up on, well, they're really interested in calculating probability and learning how to do that in mathematics courses on statistics. And as I'm going to say all the time, we're going to be more consumers of probability than computers of it, okay? So anyway, when you talk about probability, it's inevitable in textbooks and in teachers giving presentations about it that we use cards and what's the probability of drawing certain cards or sequences of cards. So since we're going to be looking at cards in a few minutes, let's start with something a little bit more fun. Magic trick to get us started, okay? Seems like I might have shown you this trick earlier in the semester. So if you've seen it already, bear with me. And if you haven't, or if you've forgotten, let's do it again, all right? So pick a card, any card, all right? Don't dwell too long on it. Pick one card, focus on the card you've chosen. I'm flipping them over, and I'm going to remove one. There goes one card. I'm going to shuffle the remaining cards. Are you impressed with my PowerPoint? Yeah. And snap of my fingers, and your card, which has already been taken out, is your card. All right? Yours is now gone. Can you remember your card? Let's turn them back over, and presto, your card is gone, isn't it? I think I've done this already before this semester. All right. So, yes, I guarantee you that your card is gone. All right? Thank you for that applause. All right. Now, how's that done? I probably gave away the secret before too, but I'll do it again. So what you just experienced is a good example of what we call, a perfect example of what we call inattentional blindness. All right? We can't pay attention to everything that goes on around us. We'd be absolutely overwhelmed. So our brain, being the good brain that we were just talking about, liking to take shortcuts, one of the biggest shortcuts it takes is automatically filtering out what it decides is unimportant to us. So I asked you to focus on a card, and you did just that. You picked one card, and you rather more or less likely ignored all of the other cards and focused on your one card. So those were the original 6 cards that I showed you. You picked one, and then I flipped them back over, and you presumed I was being honest and flipping over the cards that were up there before, but take another look and you see that they're all different cards, okay? So everybody's card was gone because all of these are different cards. And you weren't paying attention to it. A good example of inattentional blindness, okay? I will likely put a link up on the course page to a couple other really clever, really interesting, kind of humorous examples of inattentional blindness, and go take a look at them. If you haven't seen them before, I think you'll be absolutely flabbergasted. Okay, so inattentional blindness is a fun thing. I've had a student group that studied that recently and replicated one of the studies that I might put a link up here. Great stuff. Okay, so anyway, there's a card trick to get us going talking about probability. Let's return to the topic at hand, shall we? Probability and the normal distribution. Now, for the next few, rest of the way, we're going to have a lot to say about normal distributions. They're absolutely essential, and we'll see more clearly how and why. And we're also going to be focusing on probability, not so much computing it, like I said a moment ago, but on using it. All right. So up till now, we've been concentrating exclusively on descriptive statistics, and we're turning a corner now to focus on the inferential statistics. And to remind you what they are, you don't need reminding, of course, but inferential statistics are a group of statistics that when you are interested in going from the known to understanding things about the unknown, okay? So we gather data from samples of a large population that we don't have access to, and we use that data to make predictions, inferences, judgments, decisions upon what we think the larger population from whence they came, what they will do, what they will be like, what tendencies they have, all right? So it's all about probability. We're not studying the absolute behavior of groups. We're using a sample to predict. And whenever you're predicting, you have a degree of unknown. People don't always behave like they should. So we use the laws and what we learn about probability to make distinctions about what we think people are likely to do in the future. If we gave them this treatment, or to find out if two things are correlated, what's the probability, the possibility that they're connected the way that we think they might be. So the cornerstone of inferential stats is probability. Okay, so even though we're going to spend a lot of time talking about it, even though we in psychology and many other social sciences in particular, and some of the life sciences, of course, use probability quite a bit, it's not really a natural thing for most of us, okay? Now, some of us don't think that we're very good at math, but I'll argue that you are good at math. You have evolved a nervous system. You have a brain that's evolved to express things mathematically, all right? It's kind of a universal thing. All cultures seem to stumble eventually upon at least some pretty rudimentary, if not advanced, concepts associated with math. And I don't think it's a coincidence that we happen to use a base 10 mathematics. I don't know where we would have gotten the idea to use base 10. You can have base 2 mathematics. That's a binary system like we use in computers, and you could have base 3, base 6, base whatever. All right, they're all there. They're all available. But for some reason that I can't think of, we seem to have focused on base 10. I wonder why base 10. I'll never know. Okay, so anyway, we've evolved a nervous system that is good at mathematics, but probability is an offshoot of mathematics that I don't think comes as readily, as naturally, as instinctively, if you will, to us. So let me test your ability to determine some probabilities. Okay, so here we go.
Holy heart failure!
Okay, holy heart failure. I'm going to be talking about some pretty morbid subjects here. So, the probability of dying in certain ways. Okay, so which is more likely cause of death in the United States? Being killed by falling airplane parts or being killed by a shark? Now, think quickly about that and come up in your mind with an answer to that. Sharks or falling airplane parts? Which kills more people in the U.S.? Do more Americans die from, I'm going to clump these together, so category A, homicide and car accidents put together, or a category B, emphysema and stomach cancer? Which of those do you think is a more likely source or cause of death in the U.S.? Which claims more lives in the United States, lightning or tornadoes? Lightning or tornadoes? Okay, now, what I'm guessing you probably haven't done is paused this presentation and gotten out Google and looked up the answers or figured out some way to find that answer in a more definitive sense. You certainly haven't pulled out tables of statistics and tried to calculate it yourself now, have you? So what did you turn to when you tried to answer these sorts of questions, and what did you come up with? We'll talk about that in just a second. So what are the answers to these, okay? So many of these are very odd things. I mean, getting killed by a falling airplane part or from a shark is, admittedly a very unusual way to go. The chance of dying from falling airplane parts, though, is, perhaps surprisingly enough, 30 times greater than dying from shark attacks, okay? Now, you don't often hear about either one, all right? And perhaps people who fall from falling airplane parts, it's a little bit more common. Maybe it's more so common that we don't, it's not so crazy that we don't, I don't know, I don't know why we don't hear about it, but we don't seem to hear about falling airplane parts. But it's 30 times more likely, okay? I'm not making these statistics up. Okay, we got movies of, you think of the movies Jaws from way back in the dark days of the 70s. And there's been other shark movies since. There was one or two of them that are a few years ago that come to my mind. Anyway, sharks seem to pop up. They seem to surface ever so often in our minds and in our fears. And admittedly, we're going to think about it a little bit more here in Hawaii because the possibility of having sharks swimming around us is a great deal more likely than if you were in the middle of, say, Wisconsin or Iowa or somewhere up there, okay? Now, this was a question about all people in the U.S., and so what you probably didn't do when you tried to think about how to answer this question was you also probably didn't think about it very probabilistically. You probably didn't think, most people don't. Most people didn't think like, okay, think of all of the people all over the U.S. and where they live, and the fact that a very small percentage of our population lives anywhere near sharks, all right? But everybody has airplanes potentially flying overhead. So millions and hundreds of millions of people have airplanes crisscrossing over their head virtually every day, but a rather small proportion of us are in the water and have a possibility of getting, even seeing a shark, much less getting bitten and killed by one. All right, so airplane parts are quite a bit more likely. Okay. Which kills more Americans, homicide and car accidents or emphysema and stomach cancer? If you're like most people, you probably voted for homicide and car accidents. But Americans are several times more likely to die from emphysema and stomach cancer than homicide and car accidents. Okay, so I don't have a citation to show you for that or an exact amount, but why don't we think that? Why do we think so? Why do overwhelmingly people answer this question and choose homicide or car accidents as more likely? We hear about those things all the time on the news, and so it calls to mind something that I've probably talked about earlier in the semester called the media paradox. The media paradox. Things that are in the media, that are in the news, are supposed to be just that, news, unusual, newsworthy kinds of things. So we're bombarded with news these days. I grew up, in my lifetime, we've gone from most Americans having just a small handful of channels, maybe 3 or 4 networks total on their television sets, with television news being shown only at certain hours of the day, maybe 1 hour in the evening and maybe an hour in the morning or something. I don't remember, but you didn't have 24-hour news channels. Those didn't come along until about the 90s or something, okay? And then with the advent of the internet in the mid-90s and more and more people getting internet access, people had more and more news access, and people are kind of news junkies, and many of you probably look at news all the time and are news junkies yourselves, okay? So the news has to fill itself up with things that are supposedly unusual, and then we're bombarded by them so often that's the media paradox. So things that are unusual seem so usual to us. And so we way overestimate the likelihood of these unusual things happening. And homicides and car accidents are loud and explosive and they catch your attention. Okay, emphysema and cancers, not so much. Okay, not so much. People go off and die quietly in hospitals or at home or in hospices and things like that from things like that. And we don't slow down to look at them on the road like we do when we see a car accident. And we don't switch on the news to see yet, another night of homicide news, okay? So people go off and die quietly of these things, and they kill a lot more of us than these other things do, okay? Okay, back to the next question. What claims more lives, lightning or tornadoes? This is a tough one. Both of those are pretty weird, wacky ways to go and seem highly unlikely. And most people choose tornadoes. Is that the correct answer, though? No, far more people are killed by lightning than tornadoes. Think about it this way. Again, we don't tend to think probabilistically about things. We kind of reach back in our memory and think about how often we hear about things. And you don't hear about lightning strikes, okay? You don't see them. They happen so instantaneously. You get no warning. And even if you did, if somebody does get hit by lightning, the media, as bad taste as it usually has better taste than to go out to the golf course where the guy was golfing in a thunderstorm and got struck by a lightning bolt and is now a smoldering little pile of ashes with his 3-iron laying next to him. You don't see that on the news, thankfully, all right? But tornadoes, you get a lot of warning. They cause lots of big damage. You can fly over it with a helicopter afterwards and look at all this wreckage, and it's very newsworthy, and the media just loves that, okay? They'll pay a lot of money to hire a helicopter to go fly around and look at that mess afterwards. And people love to chase them beforehand and film them. And okay? But we don't think about it probabilistically. Lightning, as you see here, strikes Earth about 100 times per second. 1001, 1002. Lightning has statistically struck Earth 200 times in the time it took me to count to 2. All right, so that's a lot more likely, a lot more chances of being hit by lightning than by rather infrequent tornadoes. Plus, tornadoes give you a heck of a lot more warning. Typically, they don't fly out of the sky like a lightning bolt does. Okay, so we don't pick these answers very often, the correct answers very often. We use some other strategies that I'll come back to in a moment. Before I go on, I want to remind you of something that we talked about, I think, when we talked about line graphs, and I think I already showed you a graph like this showing the homicide rate. And I had already made the point about how it's been declining over the last few decades, but everybody thinks that it's increasing at an astronomical rate, and it's hard not to with news like we've had in recent days and recent weeks. Homicides just really seem to be on the increase, but they statistically still are more or less in a declining state when you look at it over the course of decades. So anyway, here was the rate of homicide per 100,000 people. Okay, now I don't have yearly data to show you for the emphysema rate, but the emphysema rate in the U.S. is about 17 per 1,000. Okay, so the homicide rate peaked, as you see here, in 1980 at 10 per 100,000. And the average, I don't have it yearly, but the average across years over the decades for emphysema, I dug up a statistic and it said about 17 per 1,000 in any given year. Okay, what does that look like? Let me redraw this graph to put in the emphysema rate. Okay, so the emphysema rate there is a straight line going across all the years because I don't have yearly fluctuations to show you, but there it is, 17 per 1,000. I had to readjust the x-axis here to show you this. And look at the homicide rate. You have to get up really close and see that the year 1980, you can see it is just imperceptibly above the floor here, okay? So there's that peak rate of about 10 per 100,000 compared to 17 per 1,000. So emphysema is greatly over the homicide rate. Okay? All right. Hit the pause button and read this. This is an article from The Onion. If you're not familiar with The Onion newspaper and website, as smart people you should be. All right, it's a great thing. All right, so the world death rate holding steady at 100%. Okay. Um, um, I like the last line the best. Many are suggesting that the high mortality rate represents a massive failure on the part of the planet's healthcare workers. We haven't made a dent, the smallest dent. It still remains at 100%. The death rate remains at 100%. We haven't done anything about it. What a failure. Okay. All right, let's stop talking about morbid things and the chances of death. All right, so let me ask you another question, which is more probable here. All right. So what do you think is more probable? Words that have K in the third position of the word, or words that start with the letter K? Pause and think about that for a second. Which is more frequent in the English language? Words that start with the letter K or have K in the third position? If you're like most people, you probably guessed the wrong answer. You probably guessed the words that start with K. All right, there are about 3 times as many words that have K in the third position, however, as there are words that start with K. Why do people so overwhelmingly vote for words that start with K as being more frequent? It has to do, we're not likely, you probably didn't pause and go grab a dictionary and start counting, okay? God, that would be, you just wouldn't do that. It would be hard enough just to count the K words in the K chapter of a dictionary, if I can call it a chapter. But think about it probabilistically, all right? There's only one small chapter in a dictionary that has words that start with K, and there's 20 some other chapters that, for all the other letters in the alphabet, that are full of words and could have the letter K in the third position. So it's just overwhelmingly more likely that it would be in the third or the fourth or any position is probably more likely, not just in the third position. Okay, so people get this one wrong because why? Well, how did you think about this? You didn't go and calculate this. You didn't go and dig out a dictionary and start counting. So you started to think about words that start with K, and you can very quickly come up with words that start with K. All right, but it takes a little bit more thought to think of words that have K in some other position. All right, we're used to organizing words by how they start, not by letters in some random position elsewhere in the word. Okay, so it's harder to think of words that start with that had word K in the third position. So you just assume that since they're easier to think of, they must be more likely, and you were wrong this time. Okay, so what we did with most of these examples was to give it a nice fancy name from psychology, these mental heuristics, these mental shortcuts that we took for all of these probability questions were very likely to be from the availability heuristic category of shortcuts, all right? How available can we think of examples? Okay, how available are examples of homicide? Gosh, we see them all the time. How available are, in our memories and our examples of people getting killed by lightning? Can't think of any. So it doesn't seem very probable. Okay, so we use the availability heuristic. Sometimes that helps us. It's a good shortcut sometimes. That's why we take it. But sometimes, as you can see, it gets us into trouble. It's not always right. Okay, so probability is not something that comes naturally to us. We typically turn to other more natural things like these heuristics. So we have to study it to get a good grasp of it. Now, I keep saying that we're not going to calculate probability too much. So here we go. To calculate probability, we express it as a proportion or a p-value, sometimes called a p-value. And so p-values can range from 0 to 1, all right? That's the limit, 0 to 1. Something close to 0 probability implies that something has no chance of occurring, all right? It is impossible. Something that's impossible has a p equals 0 or 0 probability of occurring. On the other end of the other extreme end, something that's certain is going to have a p-value of 1, a proportion of 1. All right, so numbers close to 0, like 0.01, 0.05, those have those imply very low likeliness of occurrence. Numbers, p-values like p equals 0.95 or p equals 0.99. Those represent very probable or very likely outcomes. Now, we're human beings, and we don't typically, in everyday life, most of us don't run around speaking the language of probability in proportions and p-values. We're more likely to use percentages in everyday life, but in statistics, we typically stick to proportions and p-values. But sometimes we have to go out and we have to talk to the real people out there, the mere mortals. And so when we do that, it sometimes makes a lot more sense to be able to do so in their language, in the language of percentages, all right? So, p-values and proportions it's very easy to go back and forth between the two. So something with a, you just multiply the p-value by 100, all right? So move the decimal place a couple places, 2 places to the right to get the percentage. So a p-value of 0.5, right, is 0.50. That's equal to a percentage of 50%, right there in the middle. So something with a 0.5 probability is essentially a coin toss probability, all right? It's 50% chance of head, 50% chance of tails. A p of 0.1 equals 10%, right? P equals 0.05, 5%, right? So even though percentages are more likely used in everyday life, proportions are more commonly used in statistics. So I need you to be able to be conversant with p-values and proportions, but be able to go seamlessly back and forth between p-values and percentages. Now, we often have sayings like this that, sports newscasters often say things like this, and coaches when they're interviewed about, their players. That quarterback, that player gave 110% out there in the field today. It's kind of an exaggerated, right? Now, as far as a probability goes, you can't give more than 100% performance on something, all right? So having a probability greater than 0.1 is just impossible. So in other words, the probability of a probability occurring greater than 1 is 0, okay? That was funny. So in everyday, in other examples in life, we can have percentages, percentage growth of your bank account, for example, of the debt in the economy and so on, can be expressed, of course, numbers, negative percentages and percentages well beyond 100. Okay, you could have 200% growth, and I hope you do someday on your bank account. Okay, so I hope you I hope someday you have at least 300% more in your bank than you do likely right now. Okay, so you can have growth beyond 100%, but probabilities are stuck in that range from 0 to 1 as p-values, 0 to 100% as percentages. All right, we're not going to go into much depth calculating probabilities. So here's a few basic things that we need to know. I haven't yet defined what probability is. It refers to the relative likelihood of occurrence of any given outcome or event. In other words, the probability associated with an event is the number of ways that an outcome can occur divided by the total number of outcomes. So there's a verbal formula. There's a verbal way, definition of how we calculate it. Okay, the number of ways that are satisfy, that we consider a success. And sometimes it's weird to think of, if you're calculating the probability of somebody dying in a certain way, it's very strange to think of that as a success. But yes, we'll call that a success. A person dies of cancer, and you're calculating the likelihood of dying of cancer. Yes, the person successfully died of cancer, divided by all the other ways that they can die. Okay, all the possible ways that you could die. All right. So mathematically, it looks a little bit something like this. The probability, the p-value, is going to be equal to, again, the numerator is going to be some component having to do with the number of times the outcome or event can occur, divided by the total number of outcomes relatively, in the ballpark. When we say total number of any outcome can occur, it's if we're counting ways to die, we're not counting, what's the probability that you're going to eat a cheeseburger or the probability that you're going to go to the circus tomorrow. All right? Those are events and outcomes unrelated to what we're talking about here. So number of ways that satisfy the outcome divided by number of ways that can satisfy any related or relevant outcome. Okay, that seems simple, and it gets quickly very ugly after that. So we're not going to go too far in this, okay? Let's try it out here. So let's try this formula out and put some actual numbers in it. So let's say let's say that we're looking at a classroom, and there are 2 male students in the class and 16 females. If I'm standing outside and wondering what is the probability that the next person, next random person to walk out the door will be a male, I could say the chances are 2. There's 2 possibilities because there's 2 males inside out of 18 total students. So the 2 males go in my numerator, and the total number of people in the room, 18, goes in my denominator. 2 divided by 8, and we don't stop there. Remember, we don't express probability as a fraction. In stats, we never stop with fractions. We don't use fractions like 2/18. We don't go there. Well, we finish the math. 2 divided by 18 equals 0.11 forever on your calculator. And so we'll typically round p-values to 2 decimal places. That's the sort of the convention. Round them to 2 decimal places of numbers. If we have to go to 0.00011, we would go out to, as many as we need so that we could get 2 good juicy decimals. But for a number like this, rounding it to 2 is sufficient. Okay, so there's a p-value of 0.11. That's the p-value. Now, how do you explain that to a mere mortal? What does p equals 0.11 mean? 11%, right? Convert that to a percent. There's an 11% chance that a guy's going to walk out of that room next randomly. Okay, good, wonderful thing to know. Okay, let's flip it around. What if we were checking the probability of that a female is going to be the one walking out of the room next? Okay, there's 16 females in the room out of 18 people, so 16 divided by 18 is 0.88 forever, and we'll round that to 2 decimal places, so 0.89, and therefore an 89% chance that it will be a male walking out. And obviously these things need to add up. So if it's just males and females as the only 2 possibilities walking out that door, there was an 11% chance of it being male, now an 89% chance, therefore a 100% chance that it's going to be a male or a female walking out that door, not surprisingly. Okay. All right. I think you get the idea here. You can stop and look at this one, but I'm going to move on. Now I want to take it up one small notch. I want to introduce just a couple of rules for additional, the 2 next more complicated things that we can compute. So the last examples were just, what's the probability of one outcome happening? What's the outcome being male or female, all right? Sometimes we want to know something a little more complicated, like what's the probability of obtaining any one of several different and distinct outcomes. Well, we'll add all of those separate outcomes. Let me show you with an example what I mean here. So we'll call this the addition rule. So here comes the
Holy Las Vegas.
Right, holy Las Vegas. So here's where the cards come in. When you think of probability, you think of playing cards. So let's turn it into a card example, all right? So what's the probability of being dealt either the ace of spades, queen of diamonds, or the king of clubs, all right? So any one of those distinct cards. So one of those 3 cards. So how do you calculate that? All right, the ace of spades there's 52 decks. If we have a whole deck of cards here, there's 1 chance out of 52 that it will be the ace. There's 1 chance out of 52 that it will be the queen of diamonds, and there's 1 chance out of 52 that it will be the king of clubs. So you could calculate those 3 individual probabilities, then mash them together and add them up, or you can just put them together and do it all at one time. So there's 3 possibilities out of 52 that will satisfy this 3-part question. So 3 divided by 52 is 0.057, and I could round that to 0.06. Okay, so there's about a 6% chance of you getting one of those 3 cards randomly drawn from a good shuffled deck, full deck of cards. Okay? Let's try another one. What's the probability of drawing a face card? All right, you know what face cards are in a deck of cards? The cards that have faces on them, all right? The jack, king, or queen. We don't include the jokers. The joker's been taken out. You know, the 2 jokers that are often in a deck of cards have been removed. I'm not including jokers or any other cards that are stuffed in the deck when you buy it. All right, so what's the probability of drawing a face card? Okay, so there's a jack, king, and queen of each of the 4 suits. Right? So there's 3 plus 3 plus 3 plus 3 equals 12 cards in a deck that have a face on it. So 12 divided by 52 is 0.2308, which I'll round. I finished it this time on this screen. We'll round that to 0.23. There's a 0.23 probability of you getting a face card. Hence, 23%. You have a 23, getting close to 25%, 1 in 4 chance. There's pretty close to a 1 in 4 chance of getting a face card. Okay. Okay, poker players, what's the probability of getting a One-Eyed Jack or a Suicide King? And if there's poker players out there, you know what I'm talking about. For the rest of you that are going, a One-Eyed what now and a Suicide who? What is a One-Eyed Jack? Two of the jacks are in profile, and I don't know who standardized decks of cards, but even though they often appear, they can be different patterns. And anyway, there's some universal things about decks of cards, and so no matter how they look, two of the jacks are in profile, not facing straight on. You can see in the background here, the Jack of Diamonds is facing straight on, and you can see both of his eyes, okay? So the Jack of Spades and the Jack of Hearts both have their face in profile, and you only see one of their eyes. So we call them a One-Eyed Jack, and they're sometimes used as wild cards in poker and other games, okay? So there's two cards that are two cards in a deck. So 2 out of 52 chances of getting a One-Eyed Jack, but I also added a Suicide King. So who or what is a Suicide King? The King of Hearts is called the Suicide King. All of the kings are holding some sort of weapon, swords, spears, I don't know what else, clubs maybe. The King of Hearts is holding it sort of behind his head, but it kind of looks like it's jammed into his head, like he's jamming the sword into his head. So he's called the Suicide King. Okay, so those are the 3 cards that qualify as One-Eyed Jacks or the Suicide King. So what's the probability? It's the same as the probability we had up on the screen a moment ago. The 3 divided by 52, the 0.06. There's a 0.06 chance of getting one of these 3 cards, just like it was the original 3 cards I had up earlier. Okay, let's take it up a notch. We'll use what's called the multiplication rule to determine the probability of obtaining 2 or more outcomes in combination. So those addition rule questions were sometimes called either or questions. Okay, what's the probability of getting either the Suicide King or a One-Eyed Jack? Okay, either or questions, we use we add the individual probabilities together. Multiplication rule, I sometimes call it the AND rule. So what's the probability of getting this and that, okay? So this assumes that independent outcomes means that the occurrence of one does not change the likelihood of the other, okay? So when they don't influence each other, as you'll see in just a second, we can multiply the probabilities, the individual probabilities together. So let's try it with a card example. What's the probability of drawing the Queen of Hearts and the King of Hearts? So I'm going to pull 2 cards out of a deck. What's the probability that I'm going to first get the Queen of Hearts and then the King of Hearts? Okay, so as you can see here visually, there's only 1 Queen of Hearts in a regular deck, so there's 1 out of 52 chances of getting her. And so let's imagine I do that. I pull out a card, and I'm going to tell you, when I teach in class, I usually have my deck of cards with me, and I go through these examples holding a deck of cards. And I kid you not, this will never likely happen again in my lifetime, but one time I did this, and I swear I didn't set up the cards, and I pulled out the Queen of Hearts. I was like, oh my god, I got the Queen of Hearts. And guess what? I pulled the second card, and I got the King of Hearts. So what was the probability of that happening? Well, you can see in just a second. What is the probability? So there's 1 King of Hearts, but notice if the Queen of Hearts is already laying, or whatever card I pulled out first is laying on the table in front of me, what's left in my hand? No longer 52 cards, but now there's only 51 cards. So see, I had to adjust this probability for the second one here. That's called sampling without replacement. One possibility, though, would be for me to look at the card and put it back in and shuffle them and still have 52. That's called sampling with replacement. So it depends on how you do this, whether you're sampling with or without replacement. So I'm talking about putting one on the table and leaving, and then only having 51 in my hand for the second pull. Okay, so I had a 1 out of 52 chance for the first one and a 1 out of 51 chance for the second one. That was equal to 0.0192. And the second one had a slightly better chance because now there's 51 cards instead of 52, so it went up to 0.0196. And the last step is to multiply those two individual probabilities together to get a much smaller probability. So 0.00038, which I'll round to 0.0004. Okay, so let's turn that into a percent. It gets a little harder to do that, but like I said, multiply it by 100 or move the decimal place 2 spots over, and so that's a 0.04. There's a 0.04% chance that I would have done this. In other words, only 0.04 of 1% chance of being able to do this. It's unlikely that I will ever be able to do this in front of a class again, but not impossible. So 0.0004. Now, whenever you're doing the multiplication rule, notice that when you multiply two fractions together, you invariably will get an even smaller fraction. So the multiplication rule is definitely going to result in smaller probabilities than addition. The addition rule again was, what's the probability of getting the queen or the king? Okay, you were accepting both outcomes, and so the outcome was greater, about 0.06. About 6% of the time you can expect that outcome, getting one or the other. Okay, but to get them both together dives down to just a fraction of 1%, 0.04 of 1% chance. So multiplication results in invariably smaller probabilities, less likely. Okay, one more example. What's the probability of drawing any king and then any queen? So what's the probability of getting any one of the 4 kings and then any one of the 4 queens together, not matching them by suits or anything? There are 4 kings in the deck. There's 4 queens in the deck. If I lay one down on the table, I started with 52, and when I lay one down on the table, I've only got 51 again for this example. And so I have a 0.006 or a 0.6% chance. So a little better than half of a percent. Okay, a little better than half of a percent. Not very likely, but quite a bit better than a 0.04% chance. Okay, now, if you took math stats, you went a whole lot further than just the addition and the multiplication rule. And if you take, you can take a whole course if you're really interested. You could take a whole course in probability, and you'll invariably cover some much more complicated stuff. It really gets ugly from there. So that's as far as I need you to know here. Let's close with something just kind of for fun here. So I'm going to ask you about birthdays. This is not something you need to know, but imagine that we're sitting in a class with there's 20 or 30 of you in a class, okay? So imagine your typical class at HPU, in-person class. Look around the room. What's the probability that any 2 people in the room share the same birthday? And if you're like most people, you think that's probably very unlikely. Now, I often make this bet when I'm teaching in person, so I'm just going to walk you through let's just pretend I'm making this bet here. So I often bet that at least 2 people do share a birthday. Okay? Yes, we'll make a bet. If I'm wrong and you win the bet, I won't give you homework. That's what I tell them when I do this.
You're a blot in the name of Gotham City University. When the students find out what kind of a person you really are, they'll hate you forever.
You tell them, Robin. Okay. So, all right. If I'm wrong and you win the bet, I won't give you any homework. And if I win, well, I always have something different that I try to claim if I win the bet. Okay. So most students, if you're like most students, you probably aren't terribly worried about losing the bet. you think it's probably very unlikely that two people in a room of 20 or 30 are going to share a birthday. So how many people do you think, let me ask the question differently, how many people do you think we need to have in order to get a 50% chance? So once the odds start to favor me, so once it's greater than 50%, the odds would dip into my favor. So how many people do we need in the room for it to favor me? You can think about that too. So the answer might surprise you. If there are 23 people in the room, the odds will have dipped in my favor. Okay? So a stats class is usually capped at 20, so I'll tell you the truth is I usually lose this bet in stats. But when I do this bet in another class that's got maybe 30, I often win the bet. And sometimes I win the bet when there's fewer than 20 people too. Okay? It can happen. So it might surprise you that if you have 23 people in a room, there's a better than 50% chance that two people share a birthday. Okay? Why do we think this is so unlikely? As you're going to see in a second, calculating it is mystifyingly difficult. You would never, you'd have to be a super genius to independently discover how to calculate the probability I'm about to show you. So since most of us can't do that, we turn to some kind of availability heuristic, and we probably think, well, how often do I run into people with my birthday? And we don't very often. However, I'm starting to find that students' opinions about this are shifting. Fewer and fewer students are as surprised when they find this out, okay? And I think I know why. I think it has to do with Facebook. On Facebook, you see when other people have birthdays. So birthdays are always popping up. You always see that when you log into Facebook, who's got a birthday. And so you find out that people do have birthdays. And sometimes you see two or more people, if you have a list of friends, having a birthday on the same day. Okay? So we're far more aware of birthdays, I think, than we ever were in the past. Okay? When you talk to people in the past, it wasn't something that popped up very frequently in conversation unless it happened to be someone's birthday, yours or that person's birthday. Like, hey, how you doing? Hey, pretty good. It's my birthday today. Oh, wow, hey. Okay? It doesn't really, when you meet someone, hey, my name's so-and-so. Hey, when's your birthday? It's not something that pops up very early in conversations typically. And so we ran around for the most of up until recently, not really knowing when people's birthdays are, and it wasn't on our mind, and so it didn't seem like we ran into people who had birthdays. Certainly shared with us, or two people that we're standing in front of. Okay, so it nowadays it's not so surprising with Facebook.
Watch out, Batman. This could be tricky.
Oh yes, it's tricky. How do we calculate this? So here we go. I'm going to show you before I show you the formula, let me show you a function that shows you, kind of gives away the answer to this. So you have number of people on the bottom here, and the probability from 0 to 1, 0 to 100%, if you will. These are written in p-values here. So the function grows like this. As the number of people grow, it very rapidly increases and it rises very quickly, and then before falling and leveling off to pretty close to certainty. Okay? As I just said a moment ago, you only need 22 people to get to about 50%, 22, 23 people, and the odds, as you see, are greater than 0.5. Okay, get up to a class of 30, and I have about I have about a 70% chance of winning that bet when there's 30 people in the room. If there's a few extras in the room, if I've got 34 people in the room, it's up to 80. See, it rises very quickly. And once you get 41 people together, there's a 90% chance that two of them are going to share a birthday. Now, when I say share a birthday, I don't necessarily mean the year too, okay? I don't mean the year. So I mean April 16th. If you have a birthday today, it's April 16th. It doesn't matter what year. I'm not talking about the same year as well, just the same month and day. Okay. Well, how do you calculate it? Down below here is a formula for calculating this, and it's the first difficult thing you have to do. The first thing you have to do to answer this question is turn the question around. So instead of calculating the probability that someone does share a birthday, you calculate actually the probability that they have a different birthday. Okay, and so I'm not going to go through this because you don't need to know it, but it's very difficult because it uses these factorials. Okay, so the formula is 365 factorial divided by the quantity 365 minus n, meaning n how many people you're talking about, factorial time, blah blah blah. So factorials, if you haven't run into them before, 365 factorial is 1 times 2 times 3 times 4 all the way up to 365. Okay? How big of a number is 365 factorial? It's huge. You can't do this. You can't use this formula with a desktop computer. Microsoft Excel will give you an error if you try to just go to Microsoft. If you don't believe me, go to Excel and try punching in, have it calculate 365 factorial. You won't even be able to do the whole formula because it won't be able to do that quantity. Okay, the number's too big for Excel to comprehend. You need to see this number. So what is the answer to 365 factorial? Using that scientific way of expressing numbers, which we often do when numbers are so awkwardly big, it's 4.34 to the 742nd. Okay, that's a 4.34 with 742 zeros following it. You need to see this number. Here we go.
Holy hole in a donut!
That is 365 factorial. And yes, I counted my zeros. There's, what did I say, 724 of them. Okay, so that's a big number. Microsoft Excel can't show you that number. It will just fail. Now, this is where I would determine if everybody, determine what everyone's birthday is and see if we have any two people that share. So I can't do it, so we'll never know if I win the bet or not, okay? But if there's more than 20 of you, if there's more than 30 of you out there in an audience viewing this, the odds are very heavily in my favor that any two of you share a birthday. It's a lot more common than we think. But it's very difficult to calculate. So that's it for today. That's it for probability. That was a lengthy presentation, but this is a lot less than you cover in a typical math stats course. That's all I'm going to have to say distinctly about probability. See you next time.
Tune in tomorrow. Same bat time, same bat channel.